Thorium-231 decays with a half-life of 25 hours to form the daughter product proactinium-231, which has a half-life of 3.4 times 10 to the power 4 years. State the change in the composition of a nucleus of thorium-231 when it decays to become proactinium-231. One neutron of thorium-231 is transformed into a proton and ejected an electron as beta decay and an anti-electron neutrino when it is transmuted into proactinium-231. A fresh sample of radioactive nuclei material contains N0 nuclei of thorium-231 and no proactinium-231 at time t equals 0. Assume that proactinium-231 is stable. Sketch graphs to show the variation with time of the number n of nuclei in sample, which are thorium nuclei and proactinium nuclei. So since the half-life of proactinium-231 is much longer than that of thorium-231, we can assume that proactinium is stable within a time interval of 125 hours. So this will be the increasing trend. There will be proactinium and the amount of thorium will decrease. Using figure 8.1 or otherwise, deduce the age of the sample radioactive material when the number of thorium-231 to the number of proactinium-231 is 1:4. So assuming all proactinium-231 come from the thorium-231, so the current number of thorium to the original number of thorium will be 1:4. So substituting these numbers into this equation, we get the time as 50 hours. Alternatively, we can use the half-life method here, and that will give us a time of half-life or 50 hours also. For many unstable parent nuclei, the daughter product is itself radioactive. This gives rise to a radioactive series where there may be 10 or more different radioactive daughter products. The variation with time t of the percentage p of different nuclei in a radioactive sample is illustrated in figure 8.2. So the parent nuclei is a daughter nucleus, and in turn this daughter produces a further daughter. Initially, there are 1.2 times 10 to the power 15 nuclei of the parent isotope in the sample, and the daughter products are not present. The parent isotope has a half-life of 3 years, and the daughter product D has a half-life of 15 years, decaying to form further daughters S, which is stable. On figure 8.2, labeled with the letter S, the line representing the variation T of the number of nuclei of stable further daughter S. Give an explanation for your choice. So we choose S is the monotonically increasing graph. Okay, the reason is that since S is stable, its numbers should keep increasing as more D will decay to form S. State the time after which the daughter product D will have its maximum activity. So since A equals to lambda n, maximum activity is when the number of D is the largest. That is almost 9 years. So calculate the maximum activity in microcuries of the daughter product D, given that 1 microcurie equal to 3.7 times 10 to the power 4 becquerel. So A is lambda n. So they will give us the answer of 32.3 microcurie. Suggest why the number of nuclei of the daughter product D increases to a maximum and then decreases. The number of D at any time depends on two processes. One, the rate of production of D from P, and two, the rate of decay of D to form S. So initially, process 1 is greater than process 2, so D increases. Now when D is equal to 1, when the process 1 is the same as process 2, then D will reach a maximum. And when process 1 is less than process 2, D will decrease. The relative activities of the parent isotope and the daughter products may be used as a means of determining the age of the sample. Suggest why this technique may provide reliable results for ages up to 30 years, but for an age of about 100 years, the method would be far less reliable. For a period of 30 years, the percentage of parent nuclei will have dropped to almost 0, and the percent of nuclei of daughter product D will still be about 30%. The activity from the decay of D can still be determined rather reliably. For a period of 100 years, almost all D will have decayed to S. The activity of D decreases to a very low value, which is the most constant. Thus, the relative activity of the parent isotope and the daughter product D cannot be measured reliably. Therefore, the method would be far less reliable to determine an age for about 100 years.